on this
découvrir
project
dans
like
ce
I have seen
chapitre.
on any other mission I have worked. I see personal sacrifice of so many
Nous allons
individuals
maintenant
that
aborder
my heart is
un
just
sujet
overwhelmed with
qui est assez
pride for the
étonnant,
folks on
mais
this
que l'on
program.
appelle la
Finally, also I see
concaténation.
passion. I've never seen the passion for this
Concaténation
program.
et
That's what
addition, ce
helps with
sont
the first two
deux
things I
notions
mentioned.
complètement différentes
Finally,
dans tous les langages de
I just see the
programmation.
faces of all our
Addition
individuals who have worked in
concerne
this program,
du
both
numérique
past
et la
and the present.
concaténation
And I can,
concerne des
neither
chaînes de
myself nor
caractères.
NASA will ever be
Prenons
able
un
to
petit
thank
exemple
these
en
persons
JavaScript
enough.
pour s'éclairer la
And
lanterne.
finally, on a more
Imaginons
personal
que
note,
j'écrive var
the web team itself,
une
we are all
valeur
going to be
égale 5.
bonded for the rest of our
J'écris
lives
var
by the web
une autre valeur
experience.
égale 5.
And I have to thank you
Si je
for the
dis à
privilege
l'ordinateur,
that you have allowed
affiche-moi
me
une
to be
boîte
part
de
of that
dialogue
experience.
avec
Thank you.
le résultat de l'addition, de une valeur plus une autre valeur. Qu'est-ce que je fais? Eh bien, je fais une addition.
All right. Thank you and congratulations, gentlemen, and congratulations to all of you once again. Today we celebrate you and your achievements. Now listen, I'm sure you're excited to see exactly what WEBB will show us. So here's the plan. We're going to take a quick break, but as you all at home can see the countdown clock, we're literally minutes away from the reveal. Are you all still excited?
Je mets les valeurs entre guillemets. Bien, si je mets les valeurs entre guillemets, je dis à l'ordinateur que
It
le
has
5
been
doit
my
être considéré
absolute pleasure
non plus
spending
comme
this
une
time
valeur
with you. We
numérique,
can't wait to
mais
share
comme
what
une chaîne
humankind
de
is capable of,
caractères.
and we are
À ce
just
moment-là,
getting
je suis
started.
à la
Let's
tête
enjoy this
de deux
journey.
variables,
Now, on the
une
count
une
of
valeur,
3, I want you
contenant
all to
le chiffre
scream,
5,
go
mais lu comme
WEBB.
si c'était une
1,
lettre de l'alphabet,
2,
et
3,
une autre variable,
go
donc,
WEBB!
qui elle aussi est égale à 5. Si je dis alerte une valeur plus une autre, j'utilise les mêmes symboles, plus dans les deux cas, mais là, je vais obtenir un résultat tout à fait étonnant, à savoir que je vais obtenir 55. Alors que s'est-il passé? Eh bien, il s'est passé que, étant donné qu'il s'agit là de deux valeurs de type chaîne de caractères, puisque l'ordinateur a mis bout à bout les deux valeurs au lieu de les additionner en termes arithmétiques habituels d'addition. Donc, faites très attention à ça. Quand vous additionnez des valeurs, suivant que ces valeurs sont numériques ou chaînes de caractères, vous obtenez, si c'est du numérique en addition au sens arithmétique du terme, par contre, si c'est une chaîne de caractères, vous obtenez une concaténation des informations qui se mettent bout à bout. Que se passe-t-il si je m'amuse à faire un joyeux mélange? Je vais écrire var une valeur égale 5, ça c'est du numérique, var une autre égale 5 entre guillemets. Et là, j'additionne les deux. J'additionne du numérique plus une chaîne de caractères. Comment va réagir notre ordinateur? Eh bien, notre ordinateur va nous dire que ça fait 55. Pourquoi? Parce que l'une au moins des deux variables est une chaîne de caractères, et bien, il considère qu'il va faire une concaténation JavaScript et bon garçon là-dessous. Il y a certains langages de programmation, vous aurez un splendide message d'erreur, du genre type Mac, c'est-à-dire vous mélangez des choux et des dérivés, donc du numérique avec du texte, donc je ne peux pas faire l'opération que vous me demandez. Nous allons maintenant voir ce que ça donnerait si je faisais var une valeur 5 et puis var une autre égale entre guillemets b. Là j'ai du numérique réellement, et là j'ai du chaîne de caractères réellement. Et je m'amuse à faire une multiplication entre la variable une valeur et la variable une autre. Comment va réagir l'ordinateur? Là, il va mal réagir, il va m'afficher un message, man, not a number, il est dans l'incapacité totale de faire la multiplication. En effet, le symbole plus sert à faire soit une addition, soit une concaténation. Le symbole multiplié, lui, ne sert qu'à faire une multiplication. Et je ne peux multiplier que des informations de même nature, à condition toutefois que celle-ci soit numérique. Donc c'est pour ça que là, je prends le message nan, not a number, je ne veux pas, je ne sais pas faire, tu mélanges des choux et des navets, c'est pas bon. Il faut savoir que lorsque vous faites une concaténation, le symbole de concaténation peut varier d'un langage de programmation à l'autre. En JavaScript, nous utilisons le plus, mais en Visual Basic, par exemple, application, nous allons utiliser le et commercial pour faire la concaténation. Donc, faites attention à cette petite nuance. D'un langage à l'autre, vous n'avez pas forcément le même symbole pour dire que vous souhaitez faire une concaténation. cas, il arrive que nous ayons une variable chaîne de caractères qui contienne du numérique. Nous allons utiliser le et que nous avons le besoin d'effectuer un calcul sur cette chaîne de caractères. Nous nous sommes aperçus que lorsqu'il s'agissait de faire des additions, on obtenait une concaténation, mais lorsqu'il s'agit de faire des multiplications ou des divisions entre différentes variables, dont l'une est en chaîne de caractères, on obtient un message d'erreur. Alors, comment faire pour malgré tout faire un calcul ? Eh bien, il n'y a pas de magie, on peut faire une conversion, à condition bien évidemment que votre variable chaîne de caractères contienne effectivement du numérique. Si j'ai la variable une valeur égale 55 entre guillemets, j'ai donc une chaîne de caractères puisqu'il y a des guillemets. Si je souhaite lire ce 55 comme étant du numérique, afin de faire une multiplication par exemple ou une division, je peux soit le faire directement, soit stocker cette valeur en tant que valeur dans une autre variable en écrivant quelque chose du genre var convertir égale number de entre parenthèses une valeur. À ce moment-là, la variable convertir nouvellement créée sera égale à 55, mais 55 compris comme étant du numérique. Et donc, si j'effectue par la suite un calcul du genre convertir multiplié par 10, le calcul pourra se faire sans aucune espèce de problème. Alors que si je fais une valeur multipliée par 10, ça risque de poser un problème. Donc, je risque d'avoir le message que nous avons vu précédemment, nan not number. Donc, là, nous pouvons convertir, nous pouvons aussi faire un calcul en disant number, une valeur multipliée par 10. Ça marcherait aussi. Le number, donc, en JavaScript, permet de convertir une variable chaîne de caractères en numérique pour peu que celle-ci contienne effectivement du numérique. Dans un autre langage, on n'utiliserait pas number, mais on utiliserait d'autres mots comme cint par exemple en VBA pour dire conversion en entier, ou cbyte pour dire conversion en byte, en octet. Peu importe le terme, le principe reste le même dans tous les langages. Une variable chaîne de caractères qui contient du numérique peut être lue comme étant numérique afin de pouvoir faire des calculs. C'est ce qu'il faut retenir de ce type de cas de figure. Alors maintenant, petite curiosité, c'est le cas où j'écris ceci. Là, j'écris if is not a number, une valeur. Alerte, ce n'est pas une valeur. Donc là, qu'est-ce que je fais ? Je fais un test de contrôle et ce test sera positif, c'est-à-dire je verrai la boîte de dialogue apparaître. Dans quel cas ? Eh bien, dans le cas où effectivement il n'y a pas de numérique dans la variable une valeur. Là, j'ai du numérique. Donc, l'ordinateur va réagir de la manière suivante. Vu que j'ai du numérique, entre guillemets, quand je dis si ce n'est pas du numérique qu'il y a dans la variable, affiche le message. Ben, moi, c'est bien du numérique, donc il n'affichera pas le message. Si je veux vraiment afficher un message sur une variable chaîne de caractères qui contient du numérique, il faut que je fasse la négation de cette condition. Et donc la négation de cette condition, c'est le fait de faire une double négation. Et donc de dire si non, ce n'est pas du numérique une valeur, affiche, c'est une valeur, et à ce moment-là, le message s'afficherait. Vous voyez, c'est un petit peu compliqué, mais bon, ça fonctionne très très bien. Je vous propose, si vous avez un souci de compréhension, de regarder dans les sources de cette formation, dans le chapitre 9, vous allez trouver tous ces petits exercices faits en JavaScript et vous verrez donc comment cela fonctionne dans votre navigateur. Voilà donc en quelques mots les différentes possibilités qui existent. Donc en résumé, une variable chaîne de caractères peut contenir du numérique. Ce numérique peut être utilisé dans des calculs pour peu qu'on le convertisse en numérique par l'intermédiaire en JavaScript de l'instruction number, mais dans d'autres langages par l'intermédiaire d'autres instructions. Si nous devons faire des comparaisons sur des valeurs chaînes de caractères pour savoir si elles sont numériques, il faut penser à utiliser des instructions de type isNaN.
Skywatchers, this is it. This is the day we get the first science images back from the James Webb Space Telescope, and you've got a front row seat to the cosmos. I'm Michelle Thaller, your host for what can only be described as a celebration for everyone on Earth. So think about this. Light from the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So longtime space fans are going to know who this is. This is Dr. John Mather. He's the senior project scientist for the Webb telescope and a Nobel Prize winner. And John, I couldn't be happier to be here with you today.
Thank you. It's a thrill to be here for this very special day.
How are you feeling?
I am thrilled and I'm relieved because you know when you start something this big, you know there's always a possibility it might not work. It did work. We are so proud.
And you've been on this project for a very long time, right?
Yeah, started in 1995. We had just finished measuring the Big Bang. We measured it with a Cosmic Background Explorer satellite that we built right here at Goddard. And we measured the spectrum. We measured there are hot and cold spots in the Big Bang. So we said, now we know it all, how it all got started. But then what happened after that? So then I got a call from NASA headquarters. Would I like to work on this new telescope that's going to help answer those questions? What happened after the Big Bang? How did the galaxies grow? How did the first black holes grow? What happened all the way from there to here? So this is our time machine, and I just wanted to be part of it. I am so thrilled that we got a chance to do it.
Yeah, one of the things that I remember you saying, and this is kind of amazing, that after you win the Nobel Prize, you thought that this mission was the most important thing to work on.
Absolutely. It's the next question. After you know how it started, what happened then? And you know, suddenly we now have the technology to do it. We didn't have 50 years ago. We didn't have the technology 25 years ago, even when we started this. We had to invent things along the way, so we did that, and here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to explore the universe. So today, the mission releases its first science images and gives wings to the dreams of so many people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused on the biggest questions in science. So the following phrase is often used too easily, but today actually does mark the dawn of a new era. Today, the Webb mission is open for scientific business, and this is just the beginning. The best is yet to come. So, John, one of the things you told me about is that you really want to make sure there are some people that get thanked, people that put a huge amount of effort into this.
Absolutely. Our current project manager, Bill Oakes, took the project from a time of trouble when we didn't exactly know how we were going to get this to work, and got it all the way to the end. Here it is working, and it's because of Bill made this worldwide team. 20,000 people around the world were involved in making this thing all work, and Bill has been there every day making sure that it would happen. So other special person is Senator Barbara Mikulski. She saved our telescope, and she saved the telescope before us. She made sure after the Hubble telescope was launched and it was not in focus that we would go up and fix it. She made sure that happened. When the Webb telescope needed more resources, she made sure we could get that. So Barbara, we thank you.
Well, it is such an honor to be with you, Jay. I mean, it's been a pleasure to be working with you through this whole thing. Thank you so much. Congratulations, and go Webb.
Thank you.
So this broadcast, much like every part of this mission, is a partnership. On our journey to explore distant places in space, we've been joined by intrepid travelers from around the globe. We have so many extraordinary collaborators. So let's check in with our partners who will be sharing the stage with us today as we reveal Webb's 5 first science images. From the European Space Agency, I'm joined by Katie Haswell in Darmstadt, Germany. Katie. I see Katie in the background there. Also joining us from the Canadian Space Agency in Montreal, we have Natalie Willette and Sarah Gallagher. Bonjour. I see Katie in the background there. I see the waving too. And so naturally, we're also going to be visiting the nerve center of this mission, the Space Telescope Science Institute on the campus of Johns Hopkins University in Baltimore, Maryland. And there we have Alex Lockwood and Carl Gordon, and they're going to give us updates and more. Good morning. Great. So we'll be back with our international partners shortly, where they'll each reveal one of the new images. But today we're also going to be joined by millions of science fans from around the world. Many are gathered at watch parties just for this event. So here we are really going international. So I'm beginning with Bhopal, India. Do we have a signal from Bhopal? Yes. Excellent. Welcome to NASA. Hello, everybody there. Wonderful to be talking to you today, all the way in India. We'll be back to them later, yes? Great to wave to you. Hi, wonderful. And we also have a warm welcome now in Portland, Oregon. So we have the feed from Portland. A bit dark, but I see everybody there. Hello, Portland. They're in an auditorium, I see. Okay, next we're going to go off to Milan, Italy. So afternoon in Italy. Do we have the feed from Italy? I guess we have a screen from Italy. And next we're going to go to Rutland, Vermont. So is this Vermont? Hello, Vermont. Hi, everybody. Nice to see you. Thank you for being part of this today. Okay, going even a little bit further afield, we have Netanya, Israel. Hello. Hello, Israel. Yay. Really nice to see you guys. Okay, and just one more for now. I see people like giving me hugs. Okay, we also have Vancouver, Canada. Hey, Vancouver. Hi. All right. Wonderful. Wonderful to have all these people with you. So right across from the campus from me, there's also a huge watch party taking place with members of the WEBB team. So the wonderful thing is that they actually are people that have worked on the mission, and they are part of our NASA Funny family. So hello WEBB team. There they are. Yes. A lot of people I recognize there. So it's incredibly important to me personally, and also to all of us at NASA, that the universe belongs to everyone. And we are thrilled to share this day with fans everywhere around the world. We'll say hello to some more later in our broadcast. So now it's time to start the main event. What you'll see over the next hour will be a collection of images newly processed by the WEBB science team. Only a tiny handful of experts have seen the images so far, and I can tell you that we have been so excited to unwrap them for everyone. We will be releasing each image in turn in real time. As soon as you see it on this broadcast, it will be available for download on the internet. On the screen below, you can see a timeline showing where we are in the show and what's coming up next. And by the end of the show, all 5 images will be available to everyone. So hopefully you can tell I'm excited. Okay, so let's do this. Okay, we're going to release the first image right here at NASA Goddard Space Flight Center, Maryland, and we're just outside of Washington, D.C. NASA Goddard is home to the project office of the Webb telescope, and the observatory portion of the telescope, the mirrors and the science instruments, were integrated and tested here before launch. So for many of us, including myself, seeing Webb come together bit by bit right in front of our eyes was an emotional and very inspiring experience. So it's kind of like a part of us was out there with Webb right now. A million miles away, part of our hopes and dreams are out there. So I'm joined now by Jane Rigby, the operations project scientist for the WEBB mission. And she's a familiar face for people who've been following this before, so welcome, Jane.
Hi, Michelle.
Okay, so Jane, you not only get the honor of revealing the first image, but this actually got a little bit of a sneak preview. I understand there was a very select audience who's already seen the image.
Yes, so last night, on behalf of the project, I had the privilege of traveling to the White House with the NASA Administrator Nelson and other senior staff to share our first image with President Biden and Vice President Harris. And it was really fun. Oh my gosh. They really geeked out. We had a closed-door session where we got to walk through all the images and just share the excitement, and they were so thrilled, and they got the profundity of what we're seeing. And so now let's do it.
Okay, we've got the whole world watching. Are you ready to put the first image up?
Oh, let's do it.
Absolutely. All right, here we go.
Okay, so the first image is a deep field. And it's also a deep field with a cluster. So why don't we walk through this just a little bit? So if we come up and look at this image, first of all, it's really gorgeous, and it's teeming with galaxies. And that's something that has been true for every image we've gotten with Webb. We can't take blank sky. Everywhere we look, there's galaxies everywhere. And so, this image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And so the cluster are all these white kind of ethereal galaxies. We're seeing them as they looked back in time. right? The speed of light is only so fast. And so as we're seeing distant galaxies out in space, we're seeing them as they looked billions of years ago. So these cluster galaxies, the white ones, we're seeing as they looked about the time the sun and the earth formed. And then behind the cluster, we have the gravity of the cluster is distorting and warping our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before. There's just a sharpness and a clarity we've never had. And so we can look at, if we zoom in on this image, and I encourage you as you grab this image at home, like zoom in. You can really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint red galaxies. Now, that was what we built the telescope to do. The most distant of those are billions of years. We're seeing as they looked more than 13 billion years ago. And so galaxies like that one right there, this little red guy, you're like, okay, yep, what is that? Well, Webb got spectra to figure out what those galaxies are made of, and this is that one. We're seeing as it looked 13.1 billion years in the past, less than a billion years after the Big Bang, and we're seeing the elements of oxygen and hydrogen as well as neon. This is how the oxygen in our bodies was made in stars, in galaxies, and we're seeing that process get started.
Yeah, I want to give this a little bit of context. So this is now the farthest away galaxy that we have this sort of detailed information about.
That we know what it's made of.
We know what it's made of.
Yes.
And this was not a long exposure for Webb.
No, the previous record holder, right, the Hubble Extreme Deep Field, was 2 weeks of continuous work with Hubble, and it was just imaging. With Webb, we took that image before breakfast. The amazing thing about Webb is the speed at which we can churn out discoveries. So everything that you're going to see here in this broadcast is a week, and we're going to be doing discoveries like this every week.
That is absolutely incredible, Jane. So thank you so much for joining us. It's been an honor to be working with you. Congratulations on all your hard work.
Thank you. It's so wonderful to see it pay off.
So thank you, and I'll see you later on today, I hope. So
yes.
Enjoy the day.
Thank you.
Right. So from distant galaxies, we now turn our eye to something a bit closer. It's a planet, but not one in our solar system. Remember that Earth and its sibling planets aren't the only show in the universe. When scientists and engineers started developing JWST, the search for exoplanets wasn't even part of the plan. That's changed. Exploring exoplanets is now a major component of the mission and the subject of our second big reveal of the day. I'm going to send it now to our friends Nathalie Ouellette and Sarah Gallagher at the Canadian Space Agency in Montreal. So again, bonjour. I guess we're having a little. We'll go.
Okay. I'm Nicole Cologne, and I'm here to tell you.
Sorry for the brief pause there. We're now going over to Canada. Okay.
Nicole's.
Yep, we're all ready. Yeah. Okay, I apologize. We're having some trouble with the signal from Canada, but luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Cologne, and she's an exoplanet scientist at NASA, and we're going to talk about this amazing new result from a very hot planet, I understand about 1,000 light years away.
That's right. The exoplanet is named WASP 96b, and it is this hot, gaseous, giant, puffy planet that it is about 1,000 light years away. So that's why today's release is so exciting, because it teases at what Webb is able to do for such a distance.
Absolutely. So talk us through what this
a very
discovery
hot
is
planet.
and why this is
I
so
understand about
significant.
1,000 light years away.
Well, this
right.
reveal that you're going to see is going to show the first spectrum
and it is this
of
hot,
an exoplanet
gaseous,
taken
giant
from the
puffy
Webb
planet
telescope.
that it is
And
about 1,000
this
light years
exciting
away. So
because
that's
it
why
covers
today's
infrared
news is so
wavelengths
exciting,
of light
because it's
that
exactly
we have not had access to before. So
Absolutely.
we've been able to use
So
other
talk us through
telescopes
what
to
this
explore
discovery
exoplanet
is and why
atmospheres
this
and
is so
infrared,
significant.
but not
1,000
to
light
this
years
level
away.
of detail.
Right.
And
The
this is
exoplanet
just
is named
one
WASP
sliver of
96b,
the first spectrum
and
that
it is
providing
this
us
hot,
using the
gaseous, giant
from the
puffy
Webb
planet
telescope.
that it is
And
about 1,000 light years
infrared
away. So
is actually
that's why
particularly good
infrared
for the spectrum.
heart
So in
just
this case,
overwhelmed with
what we're
pride.
doing is we're actually
Folks on
going to
this
take the light
program
and break it up into a rainbow
Finally,
and
also
look
I said
very, very
passion.
carefully at how
I've
much
never seen
color
the
is
passion
coming
in
in
program.
each
That's
part of the
helps with the
spectrum.
first two things
So
I
I believe we
mentioned.
have that image.
Finally,
Put that up.
tous les
Okay,
langages de
yes,
programmation.
I believe we're
faces of
revealing
all
the spectrum right
individuals.
here. So we now have our spectrum, and this is exactly what you're seeing as you just described with spectroscopy. What we did was we observed the transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you get a bunch of what looks like bumps and wiggles to some people, but it's actually full of information content. So you're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles. But what you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres, in the atmosphere of this specific exoplanet. And the other thing we can tell actually is that there's evidence of clouds and hazes because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes. Right?
Now, one thing that I really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water here, but we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 days. So it's extremely hot, extremely close in, nothing like our solar system planets. But that's okay, because what we're seeing is, again, the first exoplanet data from WEBB, and this is just the beginning. We're going to start pushing down to further smaller planets and being able to take measurements just like this with the NIRS instrument that was built by the Canadian Space Agency, but also there's three other science instruments that will add to our knowledge in the infrared, as well as direct imaging of modes, along with the transit method. So there's a lot more to come.
And I guess one thing we should mention is not only are we going to be looking at planets that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely, yes. We're going to have exciting data from planets in our solar system, from Mars outward, as well as asteroids and comets. So stay tuned for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. So we have 3 more big image reveals, and with that, new and more exciting science. But first, let's take a look back at the journey that brought us to this moment. Celebrations like this one are only possible with years of hard work from a cast of thousands. When a new mission is being built, even the most enthusiastic space fans only get to see dramatic moments in its life cycle, the news and images that come out in updates and press releases. But that doesn't really give you the sense of the huge effort that goes on behind the scenes every day. The plans, schedules, and organization to keep everything moving forward really happens, for the most part, out of people's gaze. WEBB started as an idea that took root at NASA Goddard. It grew first into planning teams, research projects, schematics, requirements. Then it began the long journey to become real with the development of new technologies, cutting-edge engineering, and finally fabrication, putting it all together. Let's take a brief look back at the visionary journey to how we all got here today.
So today was the final closeout of the purge.
Okay, guys, I can hear Rupa,
It's a pretty emotional moment to be in there and actually, you know, closing it up for the very last time, right? You know, you're the last one to touch this, and so that was the final operation. And once that fitting is closed out, there's no more touching of the vehicle. We're ready for launch.
The James Webb Space Telescope.
born from the desires of astronomers, achieved with newly invented technology, is the culmination of 20 years of work. Humanity has unlimited questions about our universe. Engineering a way to investigate them requires enormous creativity.
WEBB has been a trade-off between engineering performance, what the astronomers want, risk. In fact, when we started 20 years ago, we were actually looking at an 8-meter telescope.
Developing the most sensitive instruments. And testing, and more testing.
Between engineering performance,
and so you don't want to build one that's just incrementally better than what you've got. Because if that's the case, you would just observe longer on the telescope that you already got. And so every time NASA builds a new astrophysics mission, a new telescope, it needs to be way more sensitive, way more capable than anything we've ever built before.
We all got together in that conference room and we played real time as the images came down from the spacecraft, the very first diffraction-limited images ever obtained with WEBB. And what we collectively saw as a group was the highest resolution infrared image taken from space ever.
If you're just joining us, I'm Michelle Thaler at NASA's Goddard Space Flight Center, and you are watching live coverage of the release of the first science images from the James Webb Space Telescope. So it's appropriate now that I send the broadcast to our colleagues and friends at the Space Telescope Science Institute in Baltimore. That's the scientific nerd center of the entire Webb mission. So hello, good morning, Alex. The show is yours.
Hey, Michelle. Welcome to the Space Telescope Science Institute. I'm Alex Lockwood, and I'm here with Carl Gordon, who is an astronomer and one of the key people in delivering the images that you're going to see here today. But actually, before we get into the amazing images, we're going to talk a little bit about where we are. We're standing here outside of the Mission Operations Center, which is the key central hub for WEBB. For the past 6 months, scientists and engineers have been working 24/7 since they took control of the telescope 30 minutes after launch to prepare for today and for the amazing science to come. Through all of the major deployments, focusing, aligning the telescope, and calibrating those 4 amazing science instruments, it was all done in this building. And from here on out, we'll have daily communications with the telescope, including sending commands and downloading data with the help of the Deep Space Network. In addition to mission operations, we are also the home of science operations. Well, what does that mean? Every year, we solicit proposals from astronomers across the country and the world for what they would like to look at with WEBB. Then we hold a rigorous selection process to select the ideas that will best utilize WEBB to study and understand our universe. When the data come down and astronomers analyze their results, we are the lucky ones who get to share that data and those amazing science results with you. And we knew that today was going to be so exciting with the first images, so we've actually been preparing for years. Here is Klaus Pontoppidan, project scientist for WEBB and the technical lead for the first images,
it's been a year
to tell you about the process of the past few years of selecting the targets.
My first email related to the first images was back from 2016. So back then, a committee was created, and this committee was charged with coming up with a long list of targets for the first images. And the reason for that is that the observatory can't see the entire sky at any given time. And this is because you want to avoid the mirror seeing direct sunlight to keep it cold. And it actually had to be quite a long list. We ended up with about 70 targets, from which we had to select only a handful. What would create the most beautiful images, what would highlight the instruments, the different 4 science instruments for WEBB, and what would highlight the 4 major science themes for WEBB. And it's a celebration as well of the beginning of science observations.
And we knew that selecting the images was just the beginning, that we would need a trained eye to take these exquisite data and pull out the beauty and the science potential. So here's Jody Pasquale and Elisa Pagan to tell you about how they processed these beautiful images. And they have it up downstairs. I think they missed some of that beginning.
We're basically translating light that we can't see into light that we can see by applying color like red, green, and blue to the different filters that we have from WEBB. And the reason we want to color the images is because there's actually more that you can get, more information that you can get from the image if you see it in color.
So it's a matter of picking and choosing filters and colors that enhance the details and the structure in the image itself.
The shortest wavelengths of infrared light and assign those blue colors, and then move our way down to green and red as we go to longer and longer wavelengths.
And then we additively combine those together to get our full color image.
But there is a lot of aesthetics that are involved in this. Painstakingly going through and cleaning these images up with an attention to detail, a level of detail like at the pixel level in every image.
So when I'm working on the astronomical data, it is this sort of marriage between art and science. When you're choosing colors for the filters, you really are trying to show the different details and the processes that are happening in the astronomical images. But at the end of the day, you want it to be very compelling. You want it to be very beautiful because space is beautiful.
And after those images were processed, there was a select few of us, very lucky few of us, who got to see the first images.
Because it's downscaled by a factor of 4. Exactly. So it's just to make it a little more handy, so it's actually high resolution. So we have a team of about 30 people who are producing these images, and we feel incredibly privileged to be the ones who are the first to see these science-like images. When we saw the first data come down of real targets, people were speechless and there were emotions because we could see how amazing this observatory will be. The detail, the sharpness, the depth. And when we saw the first color images, we knew that we had a winner.
And now, we are ready to see Webb's first image of a star-dying planetary nebula called the Southern Ring. Let's do it.
Oof.
Wow, wow. This near-infrared image is, wow, the detail. Oh. Wow, okay, well, here we are. We have a near-infrared image on our left, or on maybe your right. And here on the right, we have a near-infrared image. And so I'm here with Carl, our astronomer specialist. Can you tell us what we're looking at in these images?
So this is a planetary nebula. It's caused by a dying star that has expelled a large fraction of its mass in successive waves.
Okay, so we actually see those waves in these images.
Yes.
Wow. And so there's a lot of structure. Can you tell us a little more detail about what we're looking? Maybe start with this one on the left.
Yeah. So in the near cam image, you see this kind of bubbly, almost foamy appearance throughout the whole nebula with some very structured shells. And this foaminess is showing up in orange mainly, and this is due to the molecular hydrogen that's newly formed in the expansion, just lighting up the gas and dust of this nebula. And then as we move inward, you see this kind of very blue haze in the inner region. And this is actually due to very hot ionized gas that emits well in the blue that's heated by the core, the leftover very hot core of this star.
And what about these rays that I'm seeing in this image?
Right, so there's also rays in the outer regions that you can kind of see, and these are holes in the inner nebula that are actually allowing the central star's light to come out and kind of light it up like patchy clouds with the sun shining through.
Wow, oh yeah, that's what it looks like. That's so cool. So you're actually a mid-infrared astronomer, which is different than near-infrared. And so what can you tell us about the details in this mid-infrared image?
So it looks quite different in color. partly because we're seeing different kinds of physics going on here. So we're actually seeing in the blue, you see a lot of blue. The blue is actually due to hydrocarbon grains that are emitting very strongly in the blue for MIRI. And they show the very similar structures to what we see in orange and NIRCam because the hydrocarbon, molecular hydrocarbon actually forms on the surface of dust grains. And so again, as we move inward, we see that the inner region is again hot ionized gas, but now it glows red because that's where it emits the strongest for MIRI wavelengths.
Okay.
And then as we go into the center, we see kind of the surprise for us, which is we knew this was a binary star, but we effectively didn't really see much of the actual star that produced the nebula. But now in MIRI, this star glows red because it has dust around it. So in MIRI, we got to see both stars very clearly.
Yeah, you can't see it in the first image really, but there's two stars there. So that's a fun surprise. And I think that there's another little Easter egg you want to tell us about?
Yeah, so this was, the Easter egg is this kind of narrow filament up in the top that's radially aligned. You can kind of see it very clearly in the MIRI image. It shows up as this blue structure. And it points very much to the central sources. So I thought, oh, this must just be a density enhancement in the outer nebula. I thought that very, very strongly, but other people on the team were like, no, it's a background edge-on galaxy. Well, I made a bet that said, no, it's part of the nebula. By the way, I lost the bet because then we looked more carefully at both the NIRCam and MIRI images, and it's very clearly an edge-on galaxy with a dust lane and a bulge. So I lost the bet.
Well, you lost the bet, but you got these gorgeous images, so I think it's a win for everybody.
It's a win.
Anything else you'd like to say today?
I can't wait to see where we go from here.
Neither can I. All right. Thanks so much. Back to you, Michelle.
Thank you, Alex and Carl. And I have to say that image is absolutely spectacular. So as you know, people from all over the world are watching us today and joining in our excitement as we release Webb's first science images. We've been checking in with our colleagues in Europe and Canada throughout the program, but we also want to take a moment to include the people at the so many viewing parties scattered around the world like stars in the night sky. So let's check in with some of them now. First, we go all the way to Perth, Australia. Do we have a signal from Perth? I guess nothing from Perth right now. Maybe we have some of our other feeds. We're going to check in with them right now. Do we have Winnipeg, Canada? Oh, there it is. There's Australia. There's Perth. Hey, waving to Perth, Australia. Thank you so much for joining us today. And next we're going to Winnipeg, Canada. Hello, Winnipeg. At a planetarium. Everybody's enjoying the show, I hope. Okay, Dayton, Ohio. Everybody's watching on the, there we go, Dayton, Ohio. Hello, everybody, Dayton. Nice to have you here with us. Oh, there we go. There we go, yes. Hey, hey, Dayton. Hey. They're jumping up and down. Hi. Okay, all the way Bangalore, India. Bangalore. Hello to Bangalore, India. Hey. That's absolutely wonderful. Hey. Okay, so I hope you enjoy the rest of the images we're releasing. Okay, of course, NASA's family extends all over the country. The team at JPL in Pasadena, California, they're on site to celebrate with us. So hello, JPL! Some of my favorite people in the world. Hey, hello! And I think the last place we're going to right now is Northrop Grumman, one of our major contractors. Hello, Northrop Grumman! Oh, hey, all right! Yay! Nice to see you, Northrop Grumman. All right, now there's also a big watch party right here on the NASA Goddard campus. Many of these people have worked on the mission itself, and we also have top NASA leadership and representatives from our government. So hello! Hello, watch party at Goddard. Yay! Okay, wonderful. So, I mean, at NASA, we are so fortunate to have all of these friends and colleagues around the globe. A major partner in the WEBB mission is the European Space Agency. ESA contributions have been essential to so many aspects of this project, including WEBB's spectacular launch on the Ariane 5 rocket last December. I'm very pleased to turn over the show for a few minutes to Katie Haswell. She's joining me from the European Space Operations Center in Darmstadt, Germany. Hello, Katie. Good afternoon.
Thanks, Michelle. Thank you, Michelle, and welcome to Germany. We're at the European Space Agency's
I'm still getting all kinds of IFB from lots of
centre. It's where the teams effectively fly the satellites. They're a little bit of a cross between air traffic controllers and pilots. We have lots of different control rooms here. This is the main control room, and as you can see today, it's not in use, so we've been lucky enough to move in here for today. I have two very special experts with me, both scientists from the European Space Agency. Giovanna Giardino is a near-spec scientist. Giovanna has been working on that for many years and lots to tell us about that. And Mark McCaughrean is a special advisor for space, for science and exploration. These two guys have been working on the Webb Space Telescope for a long time. So we're very grateful to have you with us. Thanks, folks.
Pleasure.
We are excited to reveal our image with you. But before we do that, we thought we'd give you a little bit of background, because we've come here today because these guys were the first ones to pick up the signal during the Webb launch, when Webb first launched. They run a system called S-Track, which is NASA's deep space tracking system, and they were listening out when Webb called home. And the controllers here have been looking after a whole very, very impressive list of missions since 1968. ESA has played a very, very important role during the Webb for the Webb Space Telescope. They provided the launch on board the awesome Ariane 5 launch vehicle from the Guiana Space Center. The atmosphere in the Mission Control Center was electric, I can tell you. I was there. They've also provided people. We have 15 ESA scientists working at Space Telescope in Baltimore, and also they have provided the infrared spectrograph, the near-infrared spectrograph, and also half of the MIRI instrument, which is the mid-infrared instrument. Let's take a look at those now.
Webb's 4 scientific instruments include NIRSPEC, the near-infrared spectrograph led by ESA. NIRSPEC splits near-infrared light from astronomical objects into its components. Like a barcode, this will help scientists understand the physics of the objects they're observing, from their temperature to atomic makeup. NIRSPEC can observe parts of an object or the sky using an image slicer and an array of microscopic shutters. Webb's integrated science instrument module, located behind the main mirror, also contains MIRI, a mid-infrared camera and spectrograph. Seen here during testing, MIRI's been developed by a partnership between Europe and the US. MIRI detects mid-infrared light from planets, stars and galaxies. It can analyse molecules to help us deduce what astronomical objects are made of and peer into clouds of gas and dust where stars and planets are born. Together, these instruments will help Webb detect and analyse light from the very dawn of time, revealing the universe as never before.
So let's get ready to reveal our image. And remember that one of Webb's jobs is to find out about galaxies, more about the galaxies, but also to help us to understand how they change. And this image is going to be very, very useful for that. Let's reveal it now. There it is. It's called Stephan's Quintet, and it's wondrous. Giovanna, what are we looking at?
Yes, like it's a quintet, so we are looking at 5 galaxies. Galaxies are this giant structure that, as we've seen, we see everywhere around us in the universe. They contain from million to 100 billions of stars, and in fact we live in one of them, the Milky Way. And here we see 5 of them. This is a closer galaxy in the foreground, and these 4 are at a distance of about 300 million light years from us, and are locked in a close interaction, a sort of cosmic dance driven by the gravitational force. you can see here these two in a process of merging within each other. This is a very important image and an area to study because it really shows the type of interaction that drives the evolution of galaxy. That's the mechanism of galaxies' growth.
I love this image of the cosmic dance moving through each other. Mark, there's a lot going on though in this image, isn't there?
There is. So this is a near-infrared image and a mid-infrared infrared image combined. And when we zoom in on the left-hand side here, we see this foreground galaxy. We see lots of individual stars in there actually resolved as point sources, which is remarkable. And then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust, which is being heated up in the collision between those galaxies. And that's a place where new stars are being born today. So we're actually seeing the process of creation of new stars in this region. And then when we look in the background here, we see not only the galaxies at 300 million light years, but also stars in our own galaxy. These snowflake structures that you see here, those are nearby stars, but in the corner and around the edges, we see galaxies which are much, much more distant, much further away. So similar in some sense to the ones that we saw earlier on in that deep field. And so this image actually takes us from the nearby galaxy, our own Milky Way, through these galaxies which are evolving today all the way to the distant universe. And in a way, it captures cosmic evolution of galaxies over those 13.8 billion years.
So we have another image, don't we, that we can
exactly.
look at?
So if we strip away the near-infrared view there of the stars predominantly, now in the mid-infrared with MIRI alone, we see mostly gas and dust. So we see the same galaxies again, the two merging, and then we also see something very interesting up at the top here because this top galaxy has something new and bright in the middle of it. And Giovanna, tell us what that is.
Yeah, that's an active black hole. We cannot see the black hole itself, but we see the material swirling around, being swallowed by these sort of cosmic monsters, and this gas gets heated to extremely high temperature as it falls onto the black hole, and it becomes very bright. In fact, this is how shiny is the galaxy. Here we see luminosity that are 40 billion times the luminosity of our suns. It's really, really bright. And with NIRSpec, we can zoom into this area, and we have this technology that allows us to take thousands of images at different wavelength channels, so see this distribution of the gas, what's going on in the gas in different regions of this core area, and understand the composition of the gas, the velocities, the temperature. So that's very important to understand the physics.
So it's giving us so much information, and it just shows the power of this telescope. Mark, this is just the beginning though, isn't it?
I think that's a very important takeaway from today. You know, these are like pictures just taken over a period of 5 days, and every 5 days we're getting more data which will contribute more in that direction. It's a culmination of decades of work, but it's just the beginning of decades. And you know what we've seen today with these images is essentially that we're ready now. This telescope is working fantastically well, and you know, to borrow a phrase from a famous rock musician, you know, we're ready to turn this telescope up to 11. It really is time. It's fantastic.
Thank you very much indeed, both of you. Back to you, Michelle.
Thanks, Katie. It is so great to have you and your colleagues with us on this historic day. So before we get to the fifth and final image reveal of the day, it cannot be said enough that an achievement like the James Webb Space Telescope is something bigger than any one of us. It's bigger than any organization, any country. This truly takes a planet. Webb belongs to all of us, and starting today, the discoveries start and they're not going to stop. This is just the beginning. We've said several times throughout the broadcast that the Webb mission is about people, and during the construction of the Great Telescope, people started to see themselves in it, literally. Day after day, people visited the observation window at NASA Goddard, and looking through the glass, they snapped selfies of themselves reflected in the gigantic golden mirror. These photos are actual reflections of the enormous human investment and the emotional commitment that brought this mission to life. And now, years later, that mission is finally collecting light from the earliest days of the universe, all the way to worlds in our own solar system. It's the same mirror that reflected the many faces who see themselves as part of the journey to understand our shared origins. Let's stop for a moment and appreciate the people behind Webb. Okay, it's time now for the last image to be revealed. Here we go. So Amber Strawn is Webb's deputy project scientist. She's here with me today to share the final big reveal of the day. So Amber, it is so good to see you. How are you feeling?
Oh, so great, so exciting. What a great day this is.
Yes, so one of the things that we're going to do is before we get to the final image, the James Webb Space Telescope has taken us all over the universe today. So let's do a quick review of where we've been so far. So Jane Rigby got us rolling today with an extraordinary new deep field image, showing us one of the farthest views of the universe ever.
Yeah, this image really does demonstrate that JWST can do exactly what we've designed it to do.
Yes. And the Canadian Space Agency then took us to the massive planet WASP 96b, where the team has detected evidence of atmospheric water.
And here again, we're seeing the incredible efficiency of this observatory. We're able to do these kind of measurements in a fraction of the time that we're able to before.
And then we zipped up the road from NASA Goddard to the Space Telescope Science Institute, where Alex and Carl showed us the exquisite Southern Ring Nebula, a mixing bowl of stellar matter around a pair of dying stars.
Yeah, and I'm just blown away by the level of detail we can see, like in the outer part of this nebula. It's incredible.
Wow. Okay. After that, it was off to Germany, where the European Space Agency wowed us with pictures of galaxies interacting and mixing together.
Right, and this image, again, it's incredible because it's showing us one of these fundamental processes of the universe, how galaxies merge together, and we're able to learn about these processes in a brand new way.
So the Webb team has a lot to cheer about right now. So across the campus, there's this big watch party, and we can feel the excitement all the way from over here. So let's join that celebration now. We're back with Senior Project Scientist John Mather, along with the head of NASA's Science Mission Directorate, Thomas Zurbuchen. Hello.
So, John, we looked around the world and we're the only ones with a cheerleading crew like over there. That's amazing. Look, you've been with this mission for decades. How do you feel today?
I am so thrilled and so relieved. This was so hard, and it took so long. It's just impossible to convey how hard it really was. That we risked so much to say we're going to go do this, and it's so near impossible, but we did it.
Yeah, there are thousands of ways this can go wrong.
Yes.
Many of them, we worried about and frankly feared even after launch. I have to tell you, I was really, really nervous. And, it's almost like athletics for me. You always get to know the team when they're on the field. And on the field, they were right after this launch, and they were perfect.
They absolutely were. And I really wasn't worried, but maybe I should have been.
Yeah, that's difference between the two of us. I always worry. I always tell everybody I'm paid to worry, frankly, and that's good. What we want to do, though, is, just really thank the team again. Of course, we heard Bill and Scott and Greg talking about the team that is there. I think what's also important is to recognize that Bernie is sitting there, who was the first manager. I was sitting there. Could you stand up? And I want to mention that Phil Sabelhaus, who is a manager also during that time, is no longer with us, but his heart is with us today.
Yeah.
I have to tell you, John, after each one of these milestones, I called a lot of people. I called Bernie, for example, and I called people at my job and people who are administrators, because there's many of them. And I just wonder how you feel about the team. Just give you the word here.
I am just so thrilled that we had a privilege to assemble such a brilliant team. We drew from the best of the best, and here we are. So my extreme deep thanks go to all the people who built that team. Not only to Bernie, who started us, to help us build up all the technology, to Phil, who made sure we would have a plan, and then when we didn't have quite enough money, to Bill, who pulled it all together and made it get all the way to the end. I am so thrilled that we had so much talent to draw on. And here we are, we have the support of the country and the world to take on this immense challenge.
You know what I'm most excited about? There's tens of thousands of scientists, and frankly, some of them just got born, or not even born, who are benefiting from this amazing telescope, because it will be with us for decades.
It will be. It took us about 25 years to get here, since 1995, and we have at least 25 to go, I hope.
So look, we are in a sense of these images, the art that is out there in the sky, revealed for the first time. We're thinking of the team and we're thanking them. John, thanks to you, thanks to all of you, and back to Michelle.
Il est opportun de donner un nom parlant qui respecte.
Thank you so much, Thomas. And this entire collection continues to just absolutely astound me. Okay, Amber, so here it is. Can you walk us through the final image reveal?
Vous faites une lettre
Absolutely.
majuscule
Here
comme
we
premier
go.
caractère de chacun des mots, sauf le premier qui est écrit en minuscule.
The last image
Et vous avez
is...
donc des noms qui
Wow,
ont un
look
sens.
at that.
Alors, nous
So,
allons
Amber,
voir
can you tell us a bit about what we're seeing here?
ce
Of
qu'est une
course.
fonction.
This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
Le premier cas de figure, vous écrivez le mot-clé function, qui est le mot
Honestly,
utilisé
it
dans la
took me a while to even figure out what to call out in this image. There's just so much going on here. It's so beautiful. One thing that really stands out to me is you sort of get this sense of depth and texture from this new data. There's a lot going on. To call out a few specifics, first of all, in general, the Carina Nebula is a nearby star-forming region within our own Milky Way galaxy, about 7,600 light years away. And in this view, we see some great examples, first of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars. We even see some galaxies sort of lurking in the background up here. We see examples of structures that, honestly, we don't even know what they are. Like, what's going on here? The data is just so rich.
And there's something really special about the infrared. Infrared can actually see deeper into these star-forming regions.
Absolutely. That's one of the great things about infrared is it really does reveal what's going on here in a really cosmic sense. And in general, what's happening in sort of this overall landscape is we have these gigantic, hot, young stars up here to the top of this rim, and the radiation and stellar winds from those stars is sort of pushing down and running into all of this. This is gas and dust. And of course, we know that gas and dust is great raw material for newborn stars and baby planets. But there's a flip side to this story and also a little bit of a mystery, because these same processes can serve to sort of erode away this material and stop star formation. So we have this sort of delicate balance going on of new stars being formed, but at the same time, the star formation is being halted. And for me, when I see an image like this, I can't help but think about scale. You know, every dot of light we see here is an individual star, not unlike our sun, and many of these likely also have planets. And it just reminds me that, you know, our sun and our planets, and ultimately us, were formed out of the same kind of stuff that we see here. We humans really are connected to the universe. We're made of the same stuff in this beautiful landscape.
And actually, the Carina Nebula was one of my favorite images from Hubble. So Hubble looked at this as well, right?
Absolutely, yeah. The Hubble image of this is also spectacular. We saw it in a different kind of light when Hubble took an image of this particular nebula. And then you can see amazing things with Hubble, but when we zoom into this new image, we're able to see so much more detail. And of course, all of us, you know, I grew up on Hubble, and all of us love Hubble. And I'm so excited to see what these two amazing observatories are able to do really in tandem with each other.
Thank you so much. And again, congratulations. It's been a pleasure to be working on this with you. I'm just amazed by what's been going on.
Thank you.
So as we're wrapping up, one of the things that I really have to say is the journey that we've been going on is so very dramatic for me. So we've gone all the way from the birth of stars, and we have all the way from the distant galaxies to the birth of stars. This is where we all began. This was the whole point of the James Webb Space Telescope, to figure out our origins from the very, very early days of the universe to star and planet formation very nearby. So right now I'm very honored to have our last special guest. This is the administrator of NASA, Bill Nelson. An honor to be with you, sir.
Hey, what a pleasure. What a banner day. It's clear that Webb represents the best of NASA. It maintains our ability to propel us forward for science, for risk-taking,
Si je veux
or
utiliser cette
inspiration.
fonction, eh bien, il me suffit quelque
And
part
we
dans
don't
mon code,
want
au
to
moment où j'en ai
ever
besoin
stop
d'écrire
exploring the
non plus
heavens,
le nom
nor
de la
stop
fonction entre
daring to
parenthèses
take
des paramètres,
another
mais de
step
mettre devant
forward
le nom
for
d'une variable
humanity.
chargée de recevoir les
In the
valeurs
words
que
of
renverra
the
cette
famous
fonction.
Carl Sagan,
Donc je mets une variable
somewhere,
adjuvante égale, je
something
mets le nom de ma
incredible
fonction,
is
entre
waiting
parenthèses
to
les
be
paramètres
known.
éventuels. Que fait
I
l'ordinateur?
think those
De là, il
words
vient
are
directement dans la
becoming
fonction, il rentre les
reality.
paramètres, le code
Absolutely.
utilise les
Thanks,
paramètres
Michelle.
et
An honor to
l'instruction
have you here.
return se
Thank you very
présente.
much.
L'instruction return se présente,
Wow.
elle renvoie des
So,
valeurs qui vont venir se stocker.
This is
à
a
l'intérieur de cette
celebration for all
variable.
humanity.
Puis le code
If you've
continuera
ever looked up at the
s'exécuter.
night sky and wonder, whoever you
Ici,
are,
de même,
wherever
lorsque
you
nous allons
are,
passer des
this
paramètres,
is
ces
your
paramètres sont
telescope.
rentrés dans la fonction.
And we also
Et lorsque
salute the
nous avons
thousands of
fini la
people who have
fonction, le
dedicated
code
part of their
s'est exécuté
lives to
tout
making
à
Web a
fait.
reality.
Donc voilà,
I also want to
très
give a big shout out for the superb media team who's helped bring Web Story to the world. This
dans
broadcast
tous
is a
les
joint
langages
effort
de
of the
programmation.
superstar producers, animators, and social media specialists at the Canadian Space Agency, ESA, NASA, and especially the Goddard Space Flight Center.
Maintenant
Web
que
captures
nous
light in
savons
distant
ce
colors
qui
that
est
the eye can't see,
fonction,
and you've actually made
je vous
this
propose
visible
de
to the world.
découvrir comment
So finally,
on
if you
peut
go to
utiliser les fonctions
nasa.gov/web
dans le
first
langage que
images,
nous
you
employons
can
pour
download
cette
all of the
formation.
images and data we've just shown in
Exemple,
full
savoir le
resolution,
JavaScript.
and check back often.
Alors,
From now on, we
lorsque
share new discoveries
nous
and exciting new
eh bien,
destinations around the universe.
nous avons
July
le code,
12th,
et ce
2022
code,
marks a huge day for
le
science.
réutiliser.
And it's only just the
Ce code,
beginning.
ça peut être
For everyone at
ici, message
CSA,
en
ESA,
alerte,
and
ce code
NASA,
de
I'm so
fonction.
very pleased you could
Ça
join
peut
us.
être beaucoup
I'm
de
Michelle Fowler.
définitions,
Go Web.
n'importe quoi d'autre, hein, c'est des instructions de programmation. Ces instructions de programmation, nous allons donc dans JavaScript, comme dire les habiller. On va d'abord les habiller avec le mot-clé function, puis nous allons donner le nom de la fonction, enfin ce nom, c'est ce que vous voulez, hein, le tout c'est de donner un nom parlant en respectant, si vous écoutez le mot, la règle visuelle, c'est de mettre le premier mot le deuxième mot avec la donc, vous pouvez demander comme vous voulez, le tout c'est que l'on comprenne ce à quoi cela sert. Cette fonction sert à faire quoi dans mon code. N'hésitez pas, hein, cassez-vous la tête, mais trouvez des noms qui expliquent bien ce à quoi sert cette fonction.